Hello everyone, my name is Kazwa Julius, and I'm going to be discussing handwritten digit cognition with MNIST dataset plus some concepts of probability. So the handwritten digit recognition is a capability of computer applications to automatically read handwritten integers from different sources, images, papers, and classifies them into predetermined classes of digits from 0 to 9. And our problem statement is we need to make this recognition of digits more understandable to the computer, because many people write in different shapes and sizes with weird handwritings. We need to make handwritings more comprehensive to the computer in a digital form. So the dataset that we're going to be using is a MNIST dataset, and its acronym. This acronym stands for Modified National Institute of Standards and Technology dataset. So we shall be using this dataset in two ways. We shall be using it to train our model and evaluate our model. Factors for choosing this dataset: basically it was free, of course. It had numerical data which I needed for my model. I needed to download the dataset, since I didn't want to waste a lot of time creating my own dataset. And this dataset has a lot of images with different handwritings of about 250 writers. And since it is easy and widely known and used, I chose to select this MNIST dataset. Its features: it has very many small images of dimensions 28 by 28 pixels, with these digits 0 to 9 being centered in each of the images. So, and this feature gives the error, it improves the error rate, and it also has over 60,000 images, of which the 60,000 has training images, and which I'll be using in my training stage, and then over 10,000 images are for testing. This very data set has a lot of images from different creators, as I have mentioned before. So it is very good. It will give us a variant and different digits, handwritten digits from different writers, which will be sufficient enough for our training of the model. For the probability concepts, I'm going to be discussing the Bayesian theorem, which suggests that a probability of a given event is based on the prior knowledge of conditions that might have been related to that event. So, and it's noted by the formulas you see above. So the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. And for the naive Bayes, it's a simple technique of constructing classifiers. And for it, it's like a simplification of the Bayes theorem, and for it, it bases on an assumption that there's a conditional so for naive Bayes, it works on an assumption that there's a conditional independence between the events. If you have A and B, they are independent of each other. So A alone can determine the output, or B alone can determine the output, since both of them are independent of the other. And we also have the Bayesian networks. For it, it is similar to naive Bayes, though for it, it takes into consideration of the conditional dependencies, where we can decide if an event is conditionally dependent on the other. Yes, and it's a graphical representation of different probabilistic relationships, which I can call the conditional dependencies among random variables in a particular set. So we have a feature of joint probability. You can have joint probabilities where one depends on the other to happen. And yes, the differences, I've discussed them previously, and here are some of the references that we used for my work that I've presented. Thank you for listening.